just to recap, we spoke about counting sets. And by that we made the following observation. We said that A is equivalent to B. Informally, they have the same number of elements. So again, number is that informal part. We don't know what number that is. If there exists, so you know the symbol means there is at least one function from f that takes A onto B, this map is bijective. That is just like when you do with fingers, 1 to 1 and onto. Right? So I pair each element from one set with a unique element from the other set B. And we observe that, that this equivalence relation is just, so this symbol is an equivalence relation. Meaning that we can say that A is identical with A. They have the same number of elements, that's by the identity map. We can say that A being equivalent to B implies B being equivalent to A, and that is the symmetry property, and then we know that A equivalent to B, B equivalent to C, implies A equivalent to C. That's the transitive property. So once we have that, we can then define what we mean to be countable, not countable, finite, etc. Right? So we will say that the set A is finite if A is equivalent to some subset 1 to all the way to n, or some n. So that's finite. Easy. Now we would say that A is infinitely countable if we can say that A is equivalent to the natural numbers, namely to the set 1, 2, 3, and onwards. Okay? And in general, we might say that A is countable if A is finite or infinitely countable. So different books have different conventions on that, but when I say countable, I mean either finite or the next best thing, identical to the natural numbers. Okay? And then of course we can make the definition of what it means to be infinite. A is infinite if A is not equivalent to any subset 1 through n, or all n. So I cannot count it by finitely many integers. Easy definition. And finally, that one is possibly strange, could such thing exist? Definition: A is not countable or uncountable if A is infinite and not countable. So fundamentally, I cannot pair it with the natural numbers. So let's consider examples. Let's just review even the examples we have done. Make sure that you understand them. So part A, well, let's try to see, that's the question, is Z countable? Right, so you see that Z contains 0, 1, 2, 3, 4, 5 onwards, but also -1, -2, -3, etc. So it's not right away, maybe it's not right away apparent that you can pair it with the integers. But here is what you can do. You can take the numbers in Z. So namely, take 0, take 1, take 2, 3 onwards, and take -1, -2 onwards in that direction. And then what do? We are gonna pair the positive numbers with the even integers. Okay? So this one will go to 2, this 2 will go to 4, this 3 will go to 6, I double it, etc. Okay, so far the function is, you can see what I did. I took all the positive natural numbers and I mapped them in a one-to-one onto fashion onto the even integers. Okay? And then what I can try to do with the 0 and negative numbers, I can map them into the odd integers. So 0 will go into 1, 1 will go into 3, this will go into 5, -2 goes into 5, etc. So this is just drawing the function without writing an explicit formula. That makes perfect sense because you can just feel that there is a function, right? The function, all it is, it's not the formula, it's really a transformation of of the elements of each element in one set to elements in the other set. Yep.
What really helped me understand it last time was when we built the your positive integers, you related it to 2n. And then you related all of your 0
right.
and below to negative 2n plus 1. It was
right?
really helpful.
You should try, in some cases the formula might be difficult, you should try to see that you're convince yourself that this works. If you feel something is fishy by this definition, maybe you feel that I first define, let's say, what the function does to 1, then what it does to 2, then what it does to 3. Maybe you feel that if I define the function consecutively, I'm never finished. Right? Some people have this computer science mind frame. So you think if I do this one by one, I will never be finished. But you imagine defining it simultaneously. So each number simultaneously knows where to go, right? So imagine all of them, they know where to stand. So there are positions 1, 2, 3, 4, 5. Each of them knows where to stand. 0 will stand at 1. 1 will stand at 2. They know where to stand. And the function that tells them where to stand might be, again, explicitly from z to the natural numbers. And the function is doing this. So it takes the integer n, and it simply doubles the integer if the integer is bigger than or equal to 1. On the other hand, if it says that the integer is less than or equal to 0, it multiplies it by -2 and adds 1. So this so the number n is non-positive. So multiplying it by -2 makes it, and adding 1 makes it a positive number clearly, and it makes it an odd number. So that defines a bijective map, as you can see. Good? That's as easy as it gets. So next part is a little bit more difficult to visualize, but let's do our best. The next part B is really important. So B is really important. So we might ask so the answer, by the way, to this is Z countable? The answer is emphatically yes. So in B, I can try to consider the Cartesian product of two natural numbers, of the two sets n cross n. Now, is this countable? Now, you have to realize that if I draw n cross n, here is how you can write the elements in it. So you can say this is 1, 1. That's the first row that begins with the first integer being 1. 1, 2, 1, 3, etc. So you can see that the first row, you can just right away see can be identified with the natural numbers. It is as large as the natural numbers. The second row will start with 2, and it is as large, it seems it contains as many elements as all the natural numbers. And you can continue. So there are integer copies of the natural numbers. Is it somehow bigger than the natural numbers? Well, based on our definition, no, because you can observe the following. So that's one argument, we'll give another, by fundamental theorem of arithmetic. Every positive integer can be expressed uniquely as 2 to the power of m minus 1 times 2 to the 2 times k plus 1, or let's not use k, let's use, since we're using n here, let's use n plus 1. So here, m and n are natural numbers. Okay? So how does this help us? Very simply, we can define a map by this fundamental theorem of arithmetic. I can define a function f from the Cartesian product of the natural numbers into the natural numbers, and the function then is defined how? It's going to send mn, so it's going to send the element in the mth row and column to 2 to the m minus 1 times 2 to the n plus 2 to the n, actually I should have said not plus 1, but rather minus 1. Otherwise, there might be a mistake. So it should be minus 1. Okay? So why does it work? Why is this function bijective? How do I know? Well, prime factorization. Any positive integer, if it's either even or odd. If it's even, there is going to be some 2 to some power that's going to be the biggest 2 that I can factor. The biggest 2 to some power that I can factor. The remaining thing will be odd. Okay? So that's why I subtract m minus 1. If the number is odd, then I select m equal 1. and that maps all the. So the first row, m equal 1, will be onto all the odd numbers. You see what the function is doing? It's taking the very first row and mapping it onto, in one-to-one fashion, all the odd numbers. And the remaining rows it will crunch based on. So the second row is mapped to all the odd numbers times 2. The third row is mapped to all odd numbers times 4. Do you see that? So what we do is I see that all the integers, all the positive integers are odd numbers. Odd when divided by 2, odd when divided by 4, odd when divided by 8, etc. Right? So that's what's happening with this function. Does it make sense? If not, we're going to still give more examples for the same phenomenon. This is going to be a very important result. Yes?
Is this always a recurring theme? Because when we looked at integers, right, we had a relationship between odd and power and even numbers, powers of 2, right? Things that we could factor 2 out of.
Well, I mean, really here, not sure if I understood or answered exactly what you are asking me, but really, it was convenient to choose 2 for this formula. Very convenient because 2 is an odd number.
The only prime.
Right, and so all the odd numbers can be expressed in this form. If you use 3, for example, then there are two types of numbers, right? If a number is not divisible by 3, then the remainder is either 1 or 2. So there are 2 types of numbers. It's a little harder to write the formula. That's really the only reason I chose 2.
So I guess my question is this a recurring theme?
Well, I'm not sure what you mean by recurring theme, right? That's the problem.
When we define bijectivity and we define these functions and formulas, will we almost always have this concept of relating some power of 2 to an odd number?
Well, notice when you define bijectivity with n, and that depends really on the problem, I think, right? There is going to be another argument I'll present that does not use the fundamental theorem of arithmetic. This itself requires a proof. Okay, so assuming you know a little bit of number theory, if this representation is unique and that comes from number theory, then this theorem is bijective. All right, so either this is surprising or not. What did we conclude? We concluded, again, yes. Again, that means that this set is as large as the set of natural numbers. So some of you might find it odd, weird, because it clearly, the Cartesian product contains many copies of the natural numbers. On the other hand, some of you might say, well, so what, it's infinity. I mean, it doesn't matter if I arrange infinity. We'll see later. So the next examples are going to be, well, a little bit beyond what we learned right now. We haven't justified everything about it, but so what about C? So we're going to show that the set of all real numbers is identical to the set of numbers between -1 and 1. Okay? So the entire bandwidth of real numbers is as numerous as just that small segment of interval from -1 to 1. Yes?
But before you move on to that, though, we can deduce immediately from this, if I'm thinking correctly, maybe I'm not, but it seems to me that it follows almost automatically from this that the rational numbers, because the rational numbers are just like n over n, right? I mean,
that's very good, exactly, right?
So the rational numbers follow directly from that. So the rational numbers are countable. Just consider that.
Well, yes, you're jumping ahead, but that's very good that you see that. Yes, the rational numbers will be countable because of this idea. That's why it's so important. Okay, but I'm going to show it later. There's going to be a very easy way to see why, because you can see this is 1 over 1, 1 over 2, 1 over 3, but then this is also 1 if you consider if you take the quotient 2 over 2. It's the same as 1. So in some ways, if you are doing overcounting if you're using it. So I'm gonna have to argue why doing overcounting is not a bad thing. But you're absolutely right. That's going to be that's why it's important. It's going to show why the rational numbers are countable. So now we just try to see why R is as numerous as the set has the same cardinality. Cardinality meaning the equivalence class, right, of things that can be put into bijection. Sets that can be put into bijection. So for -1 to 1, this is the same as R, even though this is a subset. Okay? So here is how we can do that. So I can define a function f from R to -1, 1. And you have plenty of functions that do that, but I'm going to choose this function. I'm going to choose the function f of x equal to x divided by root of 1 plus x squared. Okay? This function will do the job. How do I know? I can find an inverse for this function. You see that it works for all real numbers. We learned that I can plug a real number, I can divide by a real number as long as it's not 0, and I can take square roots, any roots in fact. Right? So this function is well defined on the real numbers, and it has an inverse. So I can take f inverse from the interval -1 to 1 to R. Just verify that they're inverses of one another, and the map is given by f inverse of, let's say, y being between -1 and 1. It's going to be equal to y divided by root of 1 minus y squared. So those maps, if you compose them in any order, they cancel one another. Okay? So you can see that this function is defined for any number between -1 and 1. And by composing one to the other, I see I get the identity. That means they are inversions. So in other words, what we conclude is that f is bijective. Now it's immediate from this f, it's immediate that we can do the following. Therefore, I can say that R is equivalent to -1 to 1, which is equivalent to the interval 0 to 1. Now you can see which maps can do that. So I can start with R, and I can apply the map F to get the interval -1, 1. Okay? Then what do I do? Then what I do from here to get to 0, 1, I just map x to x plus 1 divided by 2. You see, x plus 1, shifting it 1 unit, now I'm in the interval from 0 to 2, and divide by 2, you make an interval. Make sense? So this function is a bijection, easy bijection. So now we know that R is equivalent with the set 0, 1. In my notes, I used inverse tangent, but inverse tangent is slightly more mysterious function, so I decided I'll give you this. Okay?
But you're not saying that it's countable.
No, I'm not saying that. All I said is whatever, maybe it's countable, maybe not. We have to see. But we know that this R is as large as this interval. Okay.
But it's just going to be this.
So you have two bijections now. You have this bijection.
I have a composition of bijections. It's the transitive property I'm using. So this is equivalent to that. This -1 to 1 interval is equivalent to this interval. Therefore, this is equivalent to that. So I can kind of, by moving first by f and then by this other map that I didn't bother giving a name, I can just go right away to the interval 0, 1. It's equivalent. Okay? R equivalent to the interval 0, 1 is going to map later on. So now I'm going to speak about what is a sequence. Just quickly, what is a sequence? sequence in X is a function f from the natural numbers into X. So in other words, what you have is you can say f of 1. It's more common to write it as, let's say, x sub 1. So 1 relates to that one element that this sequence picked. F of 2, you can write it as just x sub 2. That just indicates what it did, right? So you're arranging them in order is the same as mapping, arranging some elements from X in order is the same as taking 1 and mapping to the guy who is first in line, 2 to the guy who is second in line, etc. Okay? So if you need to, you can just modify this to start from negative numbers. Okay? If you need to, you may modify the definition slightly so we can have maybe a function f that starts from, let's say, minus k all the way to 0, 1, 2, 3 onwards into X, right? You're just kind of starting to count for whichever reason from negative numbers, if that, or from 0 if that helps. So the idea that so notice what this means. So what this definition implies is that X is countable if and only if X is countable if and only if there exists a map F, there exists an F from the natural numbers to X that is bijection. That is a bijection. Yep. So that is the same thing as saying that X can be written as a sequence. I can arrange all the elements of X in a sequence. So that would be X sub k, where k goes from 1 to infinity. Okay? I can just assign all of them a ticket. So we're going to return to that. So very important idea of how you mean that the set is countable is that imagine you're running a DMV office, and you have tons and tons of people coming to the DMV. You have to arrange them in order. So one guy is the first, next guy is the next, and everybody who came can be arranged in this order. Nobody is outside of the queue line. Everybody is maybe has to wait a million turns, but eventually will see the bureaucrat. Okay? That's what countable set means.
Professor?
Huh?
I'm trying to visualize it with the example with the n cross n.
Right.
So would you be making like a snake? Would it be like 1, 1, 1, 2, 2, 2, 2, 1?
Yes, we're going to make
3,
that's
1.
another way of doing it. You're making a snake so that all the individuals that came, eventually they are going to see the clerk. Their turn will come.
Yeah.
Okay.
As long as you
So now that we know this, let's talk about the following observations. So we have this theorem, and we say that every infinite subset of a countable set is again countable. Every infinite subset of a countable set A is countable. Why is that true? Proof. So what we do is, let's suppose that B is a subset of A. B is infinite. Okay? Now, by the fact that A is countable, I can think of the set A as already enumerated. I can think of it as A1, A2, A3, A4. That's what it means that it's countable, right? That it's possible to enumerate it. So then what could be, B is a subset of it, it's infinite, okay? So what I can do is I can say, I'm going to do it a little slowly, but let's say that n1 is the smallest integer. It's the smallest integer such that A sub n1 is an element of B. Right, B is infinite, in particular it's not empty. So I go and I search for the first guy that is there. I must find one guy. Must be some guy. Otherwise I just run on, and it's something to think about. It's a bit it's a property of the integers, right? Integers are well ordered. If you take any subset of positive integers, there is always a smallest one. So we take it as given. Okay. So there is going to be n1 that is in B. And then the next guy. So then I can take A, remove A n sub 1. And that set is just everything in A except for that first guy. And then I can take n2. So that was 1. I can take n sub 2, smallest integer. Let's call this A1. For simplicity, smallest integer in A1, such that A n sub 2 is another element in B. Okay? I remove this one. Now the next smallest is going to be larger than this one I removed, so I go farther in the list and I pick the next one. Okay? So what would be the set B? So the set B I'm claiming is, if we continue this idea, it's going to be A n sub 1, A n sub 2, A n sub 3, etc. Okay? But if I run out of things to pick, then B is finite, but I claimed it's infinite. So I'm never running out of things to pick. Right? And you see, if you imagine this as an algorithm, of course it bothers you. If you imagine it as a computer algorithm, you think it does not stop. But this thing can be mathematically spontaneously arranged. You understand? Because you imagine that the smallest integer that corresponds to an element in B is somewhere. The next one is somewhere. The next is somewhere. They simultaneously just go to B. They know that where they have to go. So all the steps 1 through whatever, through infinity, they happen simultaneously. Each of them goes to the right place. This is a rather tricky thing. If you are interested, you should learn the axiom of choice. Okay, so that tells us that, so now we can see that it's countable. I made B equal a sequence here is 1, 2, 3. I paired B with the natural numbers. Okay? Good? Now, the next observation is, let me actually, again, I used this definition in the proof, but we're going to say the following. So I'm going to call, if I have A and B sets, I will say that A minus B, or I sometimes use the symbol A. I would prefer A minus B. This is easier for me to remember because I never remember which way the bar goes. So A remove B. This simply means the set of elements X belonging to A such that X is not an element in B. Okay? So in other words, this operation means remove members of B that are also members of A. So with this definition, I'm going to make the following theorem. So this is saying every infinite subset of a countable set is countable. I can also say that it's a really similar theorem. I can also say that every infinite subset contains a countable subset. As a countable subset. We can call it B. It's very similar to this argument, but the problem with this theorem, I no longer assume that I can list A as A1, A2, A3, etc. Okay? So what you do is, in a way, it's like I look into A and I pull something out, right? So if I pull something out, then A is not empty. So pick x1 belonging to A. In other words, pick something belonging to A. That will imply that A minus x1, if I take A and remove x1, this is not the empty set. Otherwise, A and is just containing one element. So there would be something else to pick. So that means you can pick x2 belonging to A minus x1. And then I can, similarly, I know that A minus the two things that I picked, x1, x2. This is not empty, so then I can pick x3 belonging to A minus x1 and x2. And I can continue this process, etc. So then I can set B. I never run out of elements. So I can set B equal to the set x1, x2, x3, etc. So if you are suspicious of this argument, that's very good. You're right to be so. It's a little bit weird, the argument, right? Because in this theorem, I had this property, again, I assume still something. I assume that all integers are naturally well ordered. Right? So any subset of positive integers is well ordered, and I can use, in other words, I can use that property to pick out the elements. But here, I don't tell you how exactly am I picking x1, how exactly I'm picking x2, x3, etc. Okay? So there is an axiom, it's called axiom of choice. It tells you that there is going to be a choice. It's always possible to do so. Okay? So the idea is, Bertrand also had a similar kind of a similar argument. He said, suppose you have a billionaire and he has infinitely many pairs of shoes. Okay? Now his task is to pick one representative, one shoe from each pair. That seems to be easy because, well, easy. You can pick the left shoe in each pair. Right? There is such a thing as a left shoe from each pair, and there is such a thing as a right shoe from each pair. But now suppose that each pair of shoes has a pair of socks. Okay? Now, how am I going to pick one representative from each of those sucks, right? There's no difference between left and right suck. So it seems unclear how am I going to make such a selection. Okay? So you understand what I mean, right? With the shoes, if I imagine that I give the shoes consciousness, that's what I imagine, right? And I say, left shoe, step forward. And each left shoe just responds to that command, and simultaneously each of them steps forward. So I don't need to do this infinite unending recursion, right? But how do I communicate to sucks? I don't know what's a left suck, what's a right suck, so I'm not sure what I tell them so that one steps forward from each pair. Okay? Do you see the problem? So the axiom of choice is telling you that there is something I could say to make each element step forward. Right.
I'm thinking about it as, for example, if you have an infinite set that has an oppressing quality, right, that makes it uncountable, right? You can
we don't know yet that there are uncountable sets, but okay.
But you can just pick out the, you could take out the oppressing quality and make it countable. So, for example, if you have the real numbers, which consist of the rational and the irrational numbers, and we'll probably learn later that the irrational numbers are uncountable, you can just look at the real numbers and take out all of the irrational numbers, and then you have a countably rational set.
Well, that's what this is. So you're
Exactly.
viewing this as...
I'm just trying to make sure, is that what this is saying, kind of?
This is kind of what this is saying, but you instead say everything that makes it uncountable, or basically just again, you're saying a little bit more. This is saying that there is some command. In each case, when I have an infinite set, there is some command I can give so that countably many will step forward. Okay? Cool. So this argument, again, you just imagine picking them up one by one, but picking them out one by one, it seems you have to go through infinitely many operations consecutively. Whereas in this case, it feels a little bit like maybe you can do it simultaneously. Actually, they both involve the axiom of choice.
So if there's a countable subset B, if there's a largest countable subset B, then it seems that his procedure would give us the procedure that he just suggested would give us the largest possible.
Well, when you say largest, I see what you mean in a way, but when you say largest, you have to be careful. What is largest countable? They're all the same size, right?
What is large?
Maybe what you mean is remove the minimal amount of things from a set, and what remains is countable, right? And again, what's a minimal number of things that you remove? It's a little bit weird when you have infinity, because again, you compare them. What's the measure of comparison is just a function, bijectivity. So by that sense, as we saw, the entire real number line is not bigger than just a small part of it from -1 to 1 or from 0 to 1. You see, that's a little weird. You would think that R is bigger, that's what you're saying, R is bigger, but it's not. According to this definition, I don't know what you mean by bigger, what you mean by smaller. Anyhow, so hopefully this is intuitive enough that you kind of take it, you believe in this part, but this is actually something that is a bit troubling in the theory. So what we have shown, in fact, is we have shown that, I'm not going to write it since I haven't yet mentioned what we mean by small or by larger in terms of this cardinality, but in a way, countable infinity is the smallest infinity there is. In other words, whenever you find infinity, a countable infinity is always its subset. And any countable subset never has any other type of infinite subset. That's what the first part tells us, right? So if we take a countable set and try to pick any of its subsets, we will never have something that is different from countable. Make sense? So now finally, again, we're gonna talk about equivalence between the Cartesian product of two sets of natural numbers with the natural numbers. So again, another argument. For n cross n. I'll just write it so it's simpler. I see this can be just simply written as natural number squared that this is equivalent to the natural numbers. So the argument goes as follows. So I just take the set 1, 1, 1, 2, 1, 3, 1, 4, and onwards, right? That's the first row. I can take the second row and I can write it as 2, 1, 2, 2, 2, 3, and onwards. The next row will be 3, 1, 3, 2, and onwards. And the next row is 4, 1, and onwards. And now I can observe the following regularity. Let's look at the diagonals. So the first diagonal, sum is 2. Look at this diagonal, the one I'm going to write. So look at this diagonal. What's the sum? The sum is 3. The next diagonal, look at it. The next diagonal consists of 3 elements. First one consists with 1 element, next with 2, next with 3. Notice the sum is 4. So third diagonal, the sum is 4. Fourth diagonal, its sum is 5. You see that? 4 plus 1. If I move 1 up and 1 to the right, it's as if I just give one integer from the first number to the second number. So you see that you can go by the diagonal. So I can say order the first diagonal, then order the second diagonal in this fashion, then order the third diagonal, and fourth, and onwards. And you can write an explicit formula for this. This is going to be, I'm going to just write it out, and you decide why this is true. I hope you can see this. So the map here is from the natural number squared to the natural numbers. And the map that I specified is doing the following thing. It's mapping m and n to m plus n minus 2 times m plus n minus 1 divided by 2. Let me erase this part. Plus n. That's what it's doing. Really what you're doing, notice that in counting, in determining where this element, let's say any element in the fourth row is. So I need to add 1 plus 2 plus 3. So you see 1 plus 2 plus 3, this ascending sum that you solved in calculus, and then plus a little bit more, that's this part, right? This part is just how do you add numbers 1 plus 2 plus 3 plus 4. That identifies when you go to the right diagonal, and then you just climb finitely many steps along that diagonal.
The only thing is when in the diagonal 2, 1, 1, 2, the arrow should only be facing one direction. Right?
So this is identified as first. This number is going to be first.
Exactly. No,
right?
my so question is why are there 2 arrows? Why are there 2 sides of the? Yeah, there you go.
This should be removed. Yes.
Yeah.
It's one arrow. Like this. Okay, so again, just to you see, this is my 1, this is my 2, my 3, my 4, 5, and 6, 7, 8, 9, 10. Okay? You can verify that this is going to be the correct formula for it. Right? If I myself haven't made a mistake, I think that's all. I say the idea very simply again, what you do is how do you find where to place an element? You note the pair and you identify in what diagonal it resides. So this is basically how many turns it has to take, because all the other diagonals had to already visit the bureaucrat. So, right? So this is the first person, second, third, all those, they visit the bureaucrat, and now I would say what's my number if I am 3 and 2, right? So then I know that 3 plus 2 is 5. I know how many came before my diagonal, and then I see my place in the diagonal. Make sense? All right, so So this example now tells us a few more interesting things. This way of counting tells us more things. So here's the theorem. The countable union of countable sets is countable.
And that'll be really similar to the first thing that we saw with the integers and the natural numbers. For example, in the first set, assign everything to an even number, and in the second set, assign everything to an odd number.
What's everything? Again, this
so the first set, let's say A and B, we have two countable sets, right?
But we have now a countable union means not just if it's A and B, then yes, you can say that. If you just have two of them, but what if you have infinitely many? Right? Countable could mean, in my language, it could be finite or infinitely countable. Okay, so so you're right if it's two of them. So again, I'll try to. Hopefully, you're seeing the picture. So what is a countable union of countable sets? So what we have is let A1, A2, A3. In this case, let's suppose that each of them is infinitely countable, right? Be countable sets. So in other words, I can then write what's happening in A1. A1, I can identify this guy as consisting, because it's countable. A1 is a countable set, so it is 1, 1, A1, 2, A1, 3, and onwards. Do you see that? So, again, what are you doing when you're trying to count things? You're trying to be an efficient manager. One famous example is, for example, the Hilbert Hotel. Right? So what you have is you have a hotel. It contains infinitely, so let's say not infinitely, it contains integer rooms. So it contains room number 1, room number 2, room number 3, room number 4, etc. Makes sense? It contains all the natural number rooms. And if a set is countable, it means that if the set is the number of guests that come. If it's countable, one guest can be assigned one room. Okay, so what is this idea? So now we have infinitely many buses coming in. So there are, let's say, sports fans. So one of them contains team A1. The next will contain team A2. Right, so since they are teams, maybe soccer teams, so each of them is wearing a mark for this first integer refers to the team. The second integer refers to the number of the player. Okay, so and onwards. You see this picture? Now you see that this matrix is exactly the same as 1, 1, 1, 2, and whatnot, right? It's exactly the same situation that we just saw before, and therefore I can arrange in rooms. I can put those players each to a unique room by the same pathway. Okay? Like this. Pretty much like in the picture over there. Now, what can we do if some of those sets are finite? Well, not a biggie. If they are finite, I can insert a lot of empty sets, so I can leave those rooms empty. Okay? So that would be just a subset. So some rooms are not occupied, but then it's only a subset of the natural numbers, which is still countable. Does it make sense?
It'll just be tougher to develop an algorithm.
It will be tougher to tell which rooms are occupied and not, but again, your purpose is only to know if the set is countable or not. So if everybody is occupying a room, then either all the rooms are occupied, or maybe some rooms are not occupied, so that then you can consider this set as a subset. No problem there. Make sense? So countably infinite already implies the situation for finite for only finite union of sets, because if you only have, let's say, up to A3, the next, you can say the next is the empty set, right? So I can still arrange the empty set, the empty members, I assign them numbers and arrange them by their proper rules. So the corollary and the corollary, one of them is that the rational numbers is countable. So that's a very, very major and far-reaching result if you're saying that it's countable. And why is it countable? Well, because again, as you noticed, I can assign pairings. I can represent the numbers of Q. So I can take Q, which is the fractions m divided by n. Let's say I can take Q plus, so I'm only using positive rational numbers, right? Q plus is m over n, m and n are natural numbers then, with n not, oh yes, that's enough, right? So if it's positive that m and n are natural numbers, that's only the positive Q. So the positive Q, I can then arrange, I can map m over n. I can map into, so I consider all possible ratios of all m to all n, and I can take those ratios just into m n. Clearly this number is going to be represented many times, right? So for example, that means that I have the number 1, 1, 1, 2, 1, 3, etc. So here I have the numbers 2, 1, 2, 2. So you can see that 2, 2 represents the same thing as 1, 1. It's the same number. It's 1, etc. But even with the overcounting, you see, the overcounting implies that in fact, let's say the integer 1 has infinitely many rooms to choose from. You can just assign, the smallest room.
But it can't repeat. It can't have 2 rooms.
Well, so what you do is once you see each rational number is actually assigned infinitely many rooms. Do you see that? Because if you take m over n, you can multiply numerator and denominator by k for k equal 1, 2, 3, 4, 5, etc. So each individual is assigned infinitely many rooms. Agreed? But this procedure is telling the possible rooms. So what he has to do is he will choose the smallest room. Okay? So once you have infinitely many room numbers, he will choose the smallest room that is going to be available. Okay? And now this way we arrange the rational numbers injectively. We are not covering all the rooms, right? Because you see this procedure still keeps plenty of rooms open. Do you understand? So not only did we push the rational numbers into this, the positive rational numbers into the natural numbers, we actually have infinitely many rooms available. So that means that the rationals in this way can be viewed as a proper subset of the natural numbers, which means that they must be countable. Every subset of natural numbers is countable. Yes? That's why it's important to see, right? So what I do with this, I identify the rational numbers with some proper subset, proper infinite subset of natural numbers. And it must be countable. Yes?
Theoretically it makes sense, but the image is a little confusing.
The image is extremely confusing, right? If you have to look at the rational numbers between any two of them, no matter how small, any two real numbers, by the Archimedean property, there is going to be infinitely many rationals. So how you assign them is really, really confusing. So now that you know that this Q plus is positive, then you know that Q minus, since it's Q minus is also countable. So Q plus is countable. Q minus is countable.
So the union of them.
And I can then add the set 0. Right? 0 is small. You see that it's at most it's countable, right? So now if I take the union of countable sets, I get a countable set. That's just using this procedure, right? So in this procedure, I can assume all the sets are infinite by adjoining empty sets, so to speak.
Professor, in the future, will we have to figure out those functions?
No, if you can draw this, it's good enough. So if you can draw it, you see, you will see examples where it's fundamentally impossible to draw. When is our class over?
6:15.
Okay.
13 minutes.
Are you still alive? You follow me? You understand what's countable and countable? It's interesting, right?
It's cool.
It's cool. It's very cool when you first look at it. If you look at it long enough, some parts might be still. You might be suspicious about parts. You might be suspicious about the axiom of choice. So some procedures that I do here, you might think, well, maybe something is fishy, but that's why it's called an axiom. You can go very deep into the logic of those things and see what you feel if it's true or not. A lot of mathematicians are kind of they are not happy with the axiom of choice, but then if you deny it, then other weird things happen. And intuitively, again, it feels like well, you see, if the set is infinite, clearly I can continue picking things out, and then I can arrange something somehow. Anyhow, so. Now, let's try to do the very weird thing. So we saw so far every set we tried to identify with the natural numbers, it ended up being countable.
Irrational.
So here we have the following theorem. This theorem tells you that R is not countable.
Yes.
So here is the proof. So we can say if R were countable, if R were countable, each subset would also be countable. So I'm a bit loose about the word countable. I mean either finitely countable or infinitely countable. Okay? So in particular, in particular, 0, 1 would be countable. So what we will observe is that we will observe this is known as Cantor's diagonalization argument. Okay, so pay attention, it's a little difficult. So what it means is suppose, so first of all we can observe that first observation is each x belonging to 0, 1 has a unique representation. Which is x equal to 0.a1, a2, a3, an, where so this is infinite expansion. Base 10, let's say. Okay? So for example, I can look at x equal to 0.5. This is not unique, but if I make it infinite, so in other words 0.4999 and onwards, right? And then now it's infinite in unique expansion. Okay, so in other words, what I mean by unique, I don't want expansions where eventually all the a sub n's are 0. You see, in this, all the a sub 2, a sub 3, etc., they're all 0. So in that case, I replace it by one where there is no largest positive a sub n. Make sense? No? That's where you have to do the homework, right? So 0.5 is a decimal representation in base 10, right? It's 5 divided by 10. 5 divided by 10 is also 4 divided by 10 plus 4 plus 9, sorry, divided by 10 squared plus 9 divided by 10 cubed, etc. Yes? So this number, x, has two expansions. One finite, in other words, after a sub 1, all the others go to 0, and one infinite, where there is no largest a sub n, after which everything is 0. That's what I mean by unique. Unique infinite representation, okay? So in your homework, you have to verify that a number can have at most two expansions, one finite, one infinite. If it has only one infinite, that's the only one in base 10. In any base P, there is one unique representation. Okay? Okay, so you understand what I mean by infinite expansion, right? So I don't see eventually 0, 0, 0, 0. Right? I always will look farther to the right and I see non-zero terms. If that is so, then each x has such a representation, and that representation is the only one it has in base 10. Okay, so then what we can do is suppose that 0, 1 is countable. So then I can list the elements as x1, and x1 I can say it's 0.a1, a11, a2, well, let's say it like this. It's going to be 0.a11, a12, a13, etc. Okay? x2, so if it's countable, I can arrange those terms in a sequence. x2 is then going to be 0.a21, a22, a23, etc. x3 is going to be 0.a31, a32, a33, etc. So then what I do is, it's called diagonalization, is I'm going to select the first term in the top sequence, the second term in the second sequence, the third term in the third sequence, and etc. I'm going to select, if I look at x sub n, it's going to be 0, blah, 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 blah. Somewhere over here it's going to be a, n, n. I'm going to select that term. So then what I do is I'm going to define y to be equal to 0.y1, y2, y3, where what I do is I'm going to say that y1 is going to be equal to, let's say, to 3 if a11 is not equal to 3. Okay? And it will be equal, and I would say that y1 is going to be equal to 2 if a11 is 3. So I'm going to just look at what happens. In general, I'm going to look at the term y sub n. It will equal to, y sub n will equal to 3 if a and n is not 3, and it's equal to 2 if a and n is 3. Okay? So that's I'll give you examples. I'm not sure you understood me with this abstract situation. Maybe I lost you completely. I don't have too much time. For now, I'll do the abstract argument. I'll repeat this when we come in class. Look at it. This y that I selected, so then y, you see it has a decimal expansion, so y belongs to the interval 0, 1. Could y be the first guy, x1? No, because look at this number, right? It differs in the first box from this number. So it could not be the first guy. Could it be the second guy? No, because it will be different in the second box. Could it be the third guy? No, it's different in the third box, etc. So it is never in the sequence. In other words, if I claim it's countable, I claim that all the numbers between 0 and 1 are arranged in order. But that is not true, because I produce another element that is nowhere in this Q line. Okay? So I claim that the workers in the 0, 1 interval, all of them are visiting the DMV office. And then I claim that all of them will have their turn. Maybe it's a billionth turn. Maybe they'll turn to dust before they go there, but they have a number. Right? My number is 1,000,001. What this argument tells you is that in fact you were not able to assign a ticket to all the people that are coming to the DMV office. It shows you how to produce one guy that hasn't been assigned a place. Do you get it? By your faces, the answer is no. So with this, we'll finish today's class, and I will return to this topic when we come back on Monday. Bye.